Okay, so we're going to go continue on the second half of chapter 4. I'm going to start on 4-10, which is types of antenna wire. So chapter 4 is, let me get the right title name of it here. It is called Propagation, Antennas, and Feed Lines. So propagation is allowing waves to propagate through space. So for example, just think of throwing a pebble into a pond. It creates waves, and those waves that move is called propagation. So when you throw the pebble into the pond, the biggest wave is right where the rock was. And then as it goes further out, the waves get smaller and smaller and smaller and fainter signal. Well, it's the same concept with the radio wave. You create a radio disturbance, and you create a disturbance in the force. Okay, literally, you create a disturbance in the electromagnetic force, and it picks up that force. The receiver will pick that up, and depending on the frequency and how distance and the obstructions between you and that receiver is how strong or how weak you're going to pick up that signal. So propagation is the idea of propagating electromagnetic waves, actually, this electro and magnetic waves, or radio waves. So you have different types of feed lines shown here on 4-7. Okay, so you have a 300 ohm twin lead. That is used really well. I remember back in the VHF TV days, UHF TV days, they would use those things to go from your roof into your TV set. They would have this 300 ohm twin lead, and it's just like a piece of black plastic, or different colors, but black, and usually there's like some kind of foam in there inside of the wire, and it keeps them separate. And that's an easy way to transmit and receive either your receiver antenna or your transmitter antenna. They use those 300 ohm twin lead. There's also a 450 ohm window line lead, which is just a little bit higher resistance and a little bit further distance apart. Then you have like coaxial cable. They have different forms of that. Coaxial means two axes. So you have a center conductor, and then you have an outside conductor. It might be the inside between the outside and the inside might be a dielectric, or it might be foam. And then they have a vinyl jacket. And there's some questions about a vinyl jacket and why it's important. So basically the vinyl jacket is to protect water from getting in. Okay, so if you get water, everyone should know by now that water and electricity don't mix. And so when you get water into your signal, it's the same thing. It's going to create problems. It can create a short. It can distort or impede your signal. And so, yeah, go ahead.
Does the outer braid carry volts, or is it just for shielding?
Yeah, the coaxial cable, it carries electricity. It can carry information, from what I understand. I could be wrong, but I think it does carry information. Maybe it just depends on the usage. It says braid shield on letter D there, and then on letter C it says conductor, outer conductor. So I think it can conduct. It could also be used for shielding, depending on what you're using. It can be aluminum. It can be copper. Different material. So I'm going to talk on 410 about SWR, which is standing wave ratio. Okay, so it's kind of hard. I wish I had some wave gimmicks or visual aids here to show you, but think of a wave. If you're in a pool and you're splashing in a certain frequency, you can see the waves will create. It'll just start forming. If you had someone over here doing it in the same frequency, you can get in sync, and if you're doing it at the same time, they can combine and create a bigger wave, or they can cancel out. If you're going in opposite, it can cancel out and interfere. So it depends on the frequency of the wave, if it's fast or slow, and whether it's going to interfere with the propagation of the wave or whether it's going to magnify it. So they have what are called SWR meters. So if you think about the length of the antenna, once it goes out of the feed line into the antenna part, it's going to create waves in the antenna. So the length of that feed line and the antenna, based on the frequency you're sending out, is either going to it's going to send the wave through it, or it's going to have some resistance. So the length of the antenna depends on how well you're going to transmit that energy out and how much is going to be stuck in the wire. So if you got a forward and a backward transmitting, they can be stuck in the wire and it can actually create some heat. And if it goes back to your radio, it can actually fry your radio. So you want to make sure you have the right length. It's called impedance match. So impedance is resistance, and you want to match the impedance based on the frequency at each end. And the idea with an SWR meter, a perfect ratio where you have the exact amount of energy being transmitted as going out is 1 to 1. And a higher number, like 2 to 1, is like half the energy is getting out. 3 to 1, 4 to 1 is even less. Okay, maybe it's more logarithmic or exponential, but less energy going out with a higher number SWR. So you want to try to get it to 1 to 1. Most radios will only accept a maximum mismatch of 2 to 1. If it's mismatched more than that, you're going to have a lot more energy coming back, which can fry your circuit. So a lot of times, I guess I haven't used the HF rigs because I don't have my general, but I understand that some of these circuits will have a protection overload, so it measures how much is coming back, and if it goes too much, it'll just cut off the transmitter so it doesn't damage the circuits. So, I'll go with some of these questions and explain them. 4-10. T4A2 says, which of the following should be considered when selecting an accessory SWR meter? So these standing wave ratio meters that measure this, they have different ranges of frequencies. So you want to make sure that you selected the right frequency when you measure it, just like you have in a multimeter. You want to select the right voltage. So something like this, you want to say, okay, I'm going to measure 10 volts, or I'm going to measure 100 millivolts. So you want to select the right frequency or the right amount before you hook it up. So you want to consider that when you're selecting an accessory meter. So T7CO4 says, what reading on an SW meter indicates a perfect impedance match between the antenna and the feed line? So 1 to 1 is the number that's a perfect match. So just remember 1 is the best, and you're trying to strive for that. Why do most solid state transmitters reduce power as SWR increases beyond a certain level? So the reason is to prevent damage. So if you increase your feedback, too much of your signal's not going out, it'll decrease the power because you can get some damage. So that's kind of the answer. And the next question is, what does an SWR reading of 4 to 1 indicate? It's an impedance mismatch, or you have a mismatch size of your antenna or length of your antenna to the transmitter. What is the benefit of a low SWR? So something like 1 to 1. The benefit is you have a lot of your power going out of the antenna and not being stuck as heat or coming back. And then what can cause erratic changes? So if you're on your meter, why would it suddenly go from 1 to 1 to 2 to 1? Why would it make it go up and down? And the answer is there might be a loose connection. So if you're out there, let's say you got an antenna on your roof and there's wind, all of a sudden you see the meter going up and down and you're like, why is it going up and down? Well, because maybe there's a wire that's loose or the wind's blowing it or something. So a loose connection can cause erratic changes in that. That's the answer to that question. What is standing wave ratio? What is SWR? It's the match between the load and the feed line impedance. So it's the load is just how much you're putting out, and then the feed line and the length of your antenna. So it's a measure of that. Okay, so now I'm going to go on to 412. Practical antenna systems. Okay, so the next part, see how we're doing on time. I got 8 minutes. All right, on this section. Practical antenna systems. Okay, so in figure 4.8, they have what's called a dipole. And it's just like a wire going up. It's the 300 ohm. This one's a 450 ohm, I can tell, because it's got the little windows in it, little air holes. It's a 450 ohm. So I can tell just because it says window from that previous page that it's a 450 ohm connector on this dipole. So dipole, 2 poles. So you basically have one wire on the left of this window looking feed going to the left and one going to the right. And it's a dipole. That's a basic dipole antenna. And again, the length matters based on what type of frequency you're going to put out. And then there's usually a center insulator. So it's just basically like, think of it as a T going up and you have one left and a right. And the way the radio wave propagates on 4-9, we have a couple of diagrams. One looks like a donut here. And then there's this other pattern. So the donut, think of the wire on the dipole is the center of that donut. And the donut is showing you how the wave is propagating out. It propagates out in the shape of a donut or a toroid, is what it's really called in geometry. So that shows you like how the wave is going to propagate out. And now if you look at it from the center of the wire and then going out the other direction, perpendicular, you'll see how it's going to transmit up and below. So it's above and below. So it'll go each side of the dipole. So that just tells you the radiation pattern of how you're going to be able to receive, and depending on which direction you want to aim it at, you might, orient it differently. So let's see. What is the disadvantage of the short flexible antenna supplied with most handheld radio transceivers compared to a full-size quarter wavelength antenna? Okay, so this one is an example of a handheld transmitter. They're also known as like rubber ducky antennas because they can bend. And they have like a little wire wrapped around, and they've got a flexible thing in the middle, probably fiberglass or something. So this is probably like, I don't know, 1/8 of a wavelength or something. It's really small. Compared to a longer antenna, I'll show you a 5/8 inch wavelength antenna for VHF. Looks like this. So it's pretty long. It's about, 4 or 5 feet long. This is a 5/8 wavelength antenna, and it's just got a simple wire, or omnidirectional. It just goes equally out like a donut around this wire. So the electricity or the wave is going to go equally out like in a donut shape on all sides. Omnidirectional means it doesn't matter which direction. So if you don't really care which direction you're sending or receiving the signal, you want to use something basic like this. If you want to aim it, there's a Yagi antenna, which is like a series of these getting smaller and smaller, and it just basically aims the wave one direction, and you point it. There's a whole horizontally polarized wave, and there's a vertically polarized wave. So if it's vertical, it's going out this direction. If it's horizontally, it's going out that direction across the horizon. So it depends on which way it's polarized and aimed. I may have talked about this before, but let's say this was my repeater up on the mountain, and here I am down in the valley, and I'm transmitting. I don't want to have my radio this way because the waves are going to go up like that, and it's not going to be as much of it connecting. You angle it this way, it's a polarization. You want to have a vertical polarization to match the vertical polarization of the repeater. So generally you want to hold your radio up because most repeaters are vertically polarized that way. So if you're doing direction, usually they'll go and do in that direction. So it just depends on, they'll use link antennas to link two different repeaters, and they may just aim them a certain direction. So what is the disadvantage of a short antenna compared to the full-size quarter wavelength? Well, it's shorter, but disadvantage is you're not getting as much of the signal, and you might get a fainter signal. Let's see. What is the disadvantage of using VHF transmitter with a flexible antenna inside a vehicle? Okay, so if I were to take this and I'm sitting in the shotgun side passenger and I'm trying to talk on it, you may be able to talk, you will, but the problem is your car usually will have like metal around it on the top and so on. And so what's going to happen is you're going to transmit, it's going to hit the roof and bounce back, and it's not really going to go out. Maybe it'll go out the sides, the windows, that sort of thing. So the disadvantage of using this inside a car is you're not going to be able to receive and transmit as well. So that's why usually you want to get something like a magnetic mounted antenna and point it on the outside. Also with this mag mount, when it attaches to the roof or wherever you're putting it on your vehicle, the roof forms what's called a ground plane. So think of it as like it's reflecting all of the waves from the top of the car back into the antenna, so you end up like receiving more. So think of it as like a satellite dish. Like your roof is kind of like collecting all that and sending it back up here to receive it. So you have to have a ground plane. Well, you don't have to, but the better the ground plane, the more energy is going to be reflected back up into your antenna, so you'll get better reception. So I could just put this on my desk if it's wood, and I'll receive something. But if I put it on something that's metal with a ground plane, I'm more likely to receive more of the signal. So let's see, what else? What is the approximate length in inches of a quarter wavelength of vertical antenna for 146 megahertz? Okay, so they have this formula. It's in, I think it's on 413. They have an example of it, but where is the actual formula? They show you an example, but I want to find that formula. I think it's like wavelength equals C over F. C is
At the top of 414,
414.
it says example to build a 2-meter ground plane
Yeah.
antenna for 146 megahertz, begin with formula
Yeah,
234 divided by 146.
there's a general form of the formula, which is lambda wavelength equals C divided by F. C is the speed of light, and F is the frequency, if I remember right. So you take the frequency divided by, maybe it's, length, the length of the antenna. So let's go back. It says length in feet. So if a resonant dipole, and then this is on 413, if a resonant dipole antenna is a half, and this says lambda, which is a wavelength, half a wavelength long, how long is that in feet? The traditional formula for thin wired dipoles that are lower than 1/2 wavelength above ground is often used, even though the estimate is usually too short at HF. So it says take the length of feet equals 468, and I don't know if that's speed of light in feet or something. I don't know what that 468, where they get that, but divided by frequency in megahertz. So example 468 divided by frequency equals the length. So 50 megahertz is your frequency. In the 6-meter band, the dipole length is 468 divided by 50, which is 9.33 feet or 112 inches long. So that's kind of generally how you figure this out, is using that formula of 468 divided by the frequency to get the length of the wave. And you can solve for that just like you can solve for voltage with Ohm's law. E equals IR. You can solve for I or R or E, depending on what you're trying to look for. If you want to solve for frequency or you want to solve for length, you can put it on either side and multiply or divide accordingly. So I talked a little bit about ground planes. Let's go to 414. They have an example here where they show like the wire, and you have this like shaded area. So that would be like the roof of your car would be that shaded area, and then that magnetic mount omnidirectional antenna pointing up would be that wire sticking up. So it basically it says electrical image. So think of your car as like the mirror, okay? So your antenna can appear twice as long because you're reflecting all that energy back into it, just like you would at a mirror. So it can increase your wavelength, and it can be a substitute for it. And they have what are called capacitance hats or ground plane radial wires here. So you can create a radial wire, radial wires, yeah. So like little wires around the base of it, which can act like a ground plane. So sometimes you might see antennas with like four little wires or like 20 or so. All that's doing is kind of trying to reflect that energy back up into the antenna. So you can substitute for the length of the antenna. You can cut your wavelength in half by putting a ground plane or putting those radial wires around it. So that's just kind of how radio waves work. All right, and here's another one. This one you just kind of have to know, 415. They're talking about CW, which is carrier wave or Morse code, and SSB, which is single sideband, which is voice. What antenna polarization is normally used for long distance CW and the SSB contacts on the VHF and UHF bands? So the polarization is basically, do you orient your antenna this way or this way? So usually they do it horizontally, that direction, because when it horizontally, it's going to hit the earth and bounce up and hit the earth and bounce up, just like skipping a rock across a pond. You want to do it horizontally. It's the same reason why when you skip a rock, you do it horizontally instead of vertically, because you're not likely to skip vertically. So the polarization is normally horizontally because it lets you go across and beyond the horizon. That's the answer for that one, is horizontal polarization. All right, the next question, T3A05. When using a directional antenna, how might your station be able to communicate with a distant repeater if buildings or obstructions are blocking the direct line of path? So there's examples of what are called Yagi antennas on the bottom of 415. There's an A and a B, and the A is a horizontally polarized, so it's kind of going horizontal across the horizon, and then figure B is vertical. So it's a bunch of those Yagis going vertical like this or horizontal like that. So the way you do it is you take like this Yagi that you're aiming your radio wave, and you aim it at something that's going to reflect the signal. So that's how you can go beyond obstructions, is you bounce it off of something. You can use the atmosphere, you can use a building, you can use a meteor, meteor scatter, propagation. There's all kinds of things you can use. If you are like, say, in the northern climes and you have the aurora borealis, those are like curtains of energized ions, and you can bounce your radio off of that, your signal, and go around obstructions through aurora borealis curtains. But the answer is, basically aim it at something that's going to reflect your radio waves. Which of the following types of antennas offer the greatest gain? I think it's Yagi, because it's directing things a certain direction. 10-9.
Circular one, because it's like the opposite of a toroid, and then it's going to send it forward.
Let me look. Yeah, it says Yagi. T9A06 in the middle of 416 is the answer. It says the most widely used type of beam antennas used by hams are Yagis. The radiation pattern for a typical beam is shown in 413. So they show you, like if you're aiming it, this is the pattern you're going to get. You can see it kind of in this reverse arrow shape. It's going outward. It's going to go that direction. So you have a little bit of it coming back. You have this little tiny little bit going back, but most of the energy is going forward. So, yeah, I don't know. So you were saying you think omnidirectional was greater gain?
Just round, like a round, perfectly round wire.
Oh, a round wire?
Mm-hmm.
I know that UHF signals in TV days, they had a round loop, and they would use that to do UHF because of its high frequency. But VHF is generally like a Yagi or something. If you
have a hard time visualizing how all these little things sticking out are sending it in that direction.
Yeah.
The circle I can get.
Yeah, so with the Yagi, basically it's like a bunch of these, like let's say this is long and this one's a little bit shorter and the next one's shorter and the next one's shorter. It's basically using this to reflect the energy back. The long beam to deflect it to the smaller beam, to the smaller, to the smaller, to the smaller, and it sort of like aims it.
And then does the center long thing, does that not send a signal?
Um,
All the little spokes are on.
Yeah, I don't know that does it. No, I don't think it does. It's more just to connect them together.
Okay.
It's really those beams that are of various lengths that's going to direct it. So if you notice, like on figure A there on 415, you notice the beam at the left is longer than the one in the right, which is towards the front. It's kind of hard to tell from this picture, but it is a little bit longer on the left than on the right, and I would say that is probably aiming to the right in that picture, so that radio wave is going to the right. Same thing on figure B. You notice, I don't know if it's very obvious from B, but the beams on the left are a little bit longer than the one on the right. It's like I said, this one's kind of hard to tell the way they drew it out, but Yagi, it was named for the inventor, so that's a common term that a lot of hams will use as a Yagi antenna. Then you have this dish on 414, which is kind of like that satellite dish type of thing. For UHF, it's a small wave, so that's a really small amount of space that you're trying to collect from, so it becomes harder to receive it. But if you aim it or point it with a dish or something, you can go a long ways. This is a 10 gigahertz example. It's like really high frequency. So, for example, cell phone towers, they use the UHF band, so they're high frequencies and they're very directed. They don't propagate very far across the horizon or anything, though. Okay, so now 417. Let's see, we're almost done. Just a couple more pages. Practical feed lines and associated equipment. So on 417, it says, which of the following causes failure of coaxial cables? So scrapes, nicks, cuts can breach the jacket. So it's that black outer jacket of the protection, and it breaches it, and then it can get water in it, which can cause it to fail. Why should the outer jacket be resistant to ultraviolet light? Well, because it's going to be in the sunlight a lot if it's outside, and there's a lot of ultraviolet light from the sun, which can cause the plastic or the vinyl to break down. So they have UV resistant coverings to prevent the water from getting in. That's why a lot of coaxial cable is black, because it's UV material that's resistant to ultraviolet light, and it breaks down slower. What is the disadvantage of air coaxial cables when compared to foam? T7C11. I think it has to do with prevents water absorption. Okay, so the foam can more easily prevent water from getting in. If it's air gapped, then the moisture can get in there and water, and it can travel further. So that's a disadvantage. It has to do with keeping the water out. Which of the following types of solder should not be used for radio and electronic applications? I think it's acid core solder. T7D08. There's two different types of solder they mentioned. There's like an acid core, and then there's another type. I can't remember, but resin, yeah.
I think acid core is used for plumbing, right?
Yeah, I think so. Yeah. So don't use the acid core one. What is the characteristic appearance of cold tin lead solder joint? I think it's like wavy molten. I want to say molten. That's not the word. It's like a blob. It's the appearance of it. Which of the following RF connector types is most suitable for frequencies above 400 megahertz? T9B06. Okay, so I'm going to go over on 417. I'm not really expert at remembering all these different types of connectors. I'm going to show you a couple of them. If I'm right, I think this one is now I can't remember if it's an RG8 or an RG58 or 59. But this is a type of connector where it's got a center core, and then it has like a screw on it. And this one is used for my UHF VHF mobile rig that I have. It can also be used to plug in. I could plug this in with an adapter. I have a picture of all the different adapters that will connect this to it. So these ones, they unscrew real easily. And there's an adapter you can get, and then you have the adapter to connect it to your unit. So you can actually do a mag mount and then bring this inside of your car and still transmit, and not have to have the problem of, trying to bounce off signals of your roof, and it's not going to go out of your car very well while you're driving. So you want a mag mount. Let's see. So they have a table here on 417, table 4.1, of the loss per 100 feet. So the greater the loss, the less signal is going to come out. And the lower the loss, the more the signal is going to come out. It also depends on the frequency. So they have a list of how much loss based on the frequency that you're transmitting is the type of connector, or type of coaxial cable, I should say. So for example, the RG58 and 59 has an impedance of 50 and 75, and you see the loss of a 50 is 2.5, whereas the loss of a 75 impedance match RG59 is 1.8. So if you're going long distances, you might choose an RG59 connector versus a 58, because you're going to have more of the signal come out at the end. Anyway. So that gives you an idea.
The best one with the least loss, but it might cost more money.
Yeah, it might cost more money. There's also other factors like if you put cables next to each other, certain types, like a coaxial cable, they won't interfere with surrounding, it won't receive interference. But the 300 ohm twin lead, like I was saying, that's susceptible to interference. It'll pick up static and things in the air, like from a lightning bolt. So if you ever remember listening to AM radio during a lightning storm, you can actually hear the lightning, because it'll strike and it'll just send out an electromagnetic wave. That lightning creates an electromagnetic wave out for hundreds of miles. And so in a lightning storm, you turn on to AM, in certain frequencies, you can hear it crackle anytime there's a lightning strike. And so it's the same thing applies with a twin lead 300 ohm. It'll pick up that signal from the lightning strike, and you might get interference. But with a coaxial, it's got a shield around it to prevent that from interfering with your signal. So the different types of cable have pros and cons. The downside is you might have a more resistance loss, but it's less susceptible to interference. All right, on 418, they have an example of all the different types of connectors. I couldn't remember any of these. I just go, see, this one looks like, BNC or an SMA. There's an NSMA. There's a UHF SMA, BNC, and then all these different types of connectors. And then there's the male and the female. So I usually just go on like Amazon or some website like hamradio.com, and I look at the connector and I'm like, all right. So the funny thing is this Yaesu has, when I unscrew it, it's got a female receiver right here, and then the antenna has a little point, so it's the male. But the Baofeng is opposite. This is the female, and that's the male. And so if I want to get a Baofeng and hook it onto my Yaesu or vice versa, I've got to get a little adapter to screw them in, because for whatever reason, the manufacturers did it opposite. So that's where these connectors come in. I don't know that they're going to ask too many questions about that, but they do show a variety of different types of connectors and adapters. So the next one, 418 at the bottom, SWR meters and watt meters. So watt meter is measuring watts or power. SWR is measuring your ratio and your standing wave ratio of your antenna and your feed line. Where should an RF power meter be installed? I want to say it's near the source. Let's see. T4A05. No, I can't find it. But okay, so figure 416, there's a question on here about where should the SWR meter be installed. When you take your radio and your antenna, you want to put it as close to your feed line, as close to your transmitter as possible. It's also more convenient. It's right there next to your radio. So what instrument can be used to determine SWR? An SWR meter. What is the major function of an antenna tuner or a coupler? It's to kind of get it tuned right so that you're putting out the most power. Let's see. Oh, another thing, I just want to mention this because my instructor mentioned this to me when I was learning ham radio. There's something called a dummy load, and I don't think there's a question on that in the technician, but there might be on the general. So if you were to like take off this antenna, turn it on, and push key it, you're sending energy out, but there's nothing to go out. There's nowhere for the electricity to go. So in a bad case, if you didn't have some kind of protection circuit, it could fry your electronics. So when you're testing your radio, they have what's called a dummy load. So you hook up like a feed line like this, and the end is called a dummy load, and it just receives all the energy. It's kind of like a resistor absorbing it. So sometimes when they're testing antennas or SWR meters or power, they'll hook it up to a dummy load, which is not going anywhere, just so that you're testing your equipment and not your antenna. So they do have that. Just wanted to mention that when I'm mentioning these types of things. All right. They call them antenna tuners. So there's SWR meters. There's also what's called an antenna analyzer, which actually has a low signal source with an adjustable frequency. So you can say, all right, I'm going to send out a bzz, and I'm going to make it different frequencies, and then it will measure how well your antenna is going to transmit that. So that's called an antenna analyzer, which is like your fake frequency generator plus the tuner part, and it can measure that. So they have an example on 418. And they have this little knob where you're adjusting which frequency you're putting through it, and then you can see how much your SWR meter is coming out based on your type of antenna. So that's it for today. Thank you for joining me, and we'll see you next week.